Hi, Alvin.
Hey, how's it going, Mark?
Okay,
Good.
I
Let
just
me just.
I lost your camera in case you were wondering.
I know, I know. I purposely did that. I'm changing my virtual background.
Right. Okay.
Mm, What I change it to? This is VTS and also ACM. So let's put it as VTS. Right. I wasn't recording, so here we go. Now I should be recording. Yeah, so welcome everyone this evening to our last IEEE Vehicle Technology Society Chicago chapter meeting, as well as ACM Chicago, IEEE Computer Society Chicago, and Mid-America Club, ITCONNECT. So thank you all for coming this evening. My name is Alvin Chin, and I'm the chair of IEEE VTS Chicago, CS Chicago, and ACM Chicago. And so today I'll be giving the last talk of this year, which is on machine learning for connected vehicles. And my day job is a AI and emerging technology researcher at BMW Technology Corporation, which is the tech office of BMW. Okay, so I'm going to give it to Kevin Studenberg, who is our vice chair, to talk a little bit about IEEE VTS Chicago chapter. So Kevin.
Hey, thanks, Alvin. Thanks again, I guess, for setting this up for everybody for attending. I am the co-chair. My name is Kevin Studenberg, the co-chair of IEEE VTS Chicago. The chair is Alvin Chen, as was mentioned. We also have a student chair that's Zero Chen, who's, I believe, on the call as well tonight. So the mission of the IEEE VTS Chicago is to create a community of academic and professionals who are interested in all things related to technology on vehicles. So thanks for attending in the discussion tonight, and hopefully there's going to be a lot of good insight that Alvin will give us all. Common topics that we have in our discussions are different sorts of connectivity, such as 5G, advanced connectivity, automated connected or electric vehicles, ACE vehicles, different sorts of DSRC communication, and how those different things impact advancing technology. So if you're interested in becoming a member, we've got a link here for joining VTS. I guess just refer to the slides or look up IEEE VTS Chicago, and you'll be able to work your way through Google to find the right links, or you can also find us on Facebook, LinkedIn, and Twitter. So thanks for joining.
All right, thank you, Kevin. So I will also want to mention too as well that Vehicle Technology Society, we have a conference that's called Vehicle Technology Conference. So it is our kind of a flagship conference. We actually have two conferences per year, one in the spring, one in the fall. Both because of COVID, they both have been virtual. So currently right now, we do have the Vehicle Technology Conference that's running until December the 16th. So that's the URL. So if you want to register, there is an associated cost to register for this, so it's not totally free. But if you're interested in wanting to know more about Vehicle Technology Society, the keynotes and papers that are presented there from academia and industry, you can go to that website. Also, what's interesting as well is that in terms of my involvement in this conference, I chaired a panel on standards for connected and automated vehicles. So I'm part of the standards committee, the IEEE standards committee for standardizing on connected and automated vehicles. And we held a panel with 4 panelists. So if you want to register, you can also have a look at that panel that we did virtually as well. Okay, and next we have is IEEE Computer Society Chicago. So we've done a lot of talks, this year together with IEEE Computer Society Chicago. So basically, we are the Chicago chapter of the IEEE Computer Society. We do lots of similar types of meetings with ACM Chicago. Hence, that's the reason why we do a lot of joint activities together. So you can see that we deal with software, hardware, computing, AI, big data, cloud computing. We've partnered with a cybersecurity company that does conferences, and so we give our members access to those cybersecurity conferences, which is very important now these days in IT. So I'm the chair also of this society, and our vice chair is Gina Martinez. And you can see our web, Facebook, Twitter, and LinkedIn. So a copy of these slides and the recording will be made available after this webinar. All right, and then next as well is to welcome the ACM Chicago members. So I'm going to turn it to Mark to explain a little bit about ACM Chicago.
Thanks. Well, ACM Chicago, we have monthly meetings. Of course, they're all virtual right now. We've been holding these since September, and we have a looks like we're going to have a full roster of monthly programs. In fact, you'll learn after the presentation about 2 meetings in January. I'm the vice chair. Alvin, as you know, is chair, and Greg Newmark, who you've already seen on screen. We're the 3 that run the organization. We're always looking for interested persons to help us. There's a lot of really great opportunities. And you can see all of our links in the slide there, where you can see most of our information. Of course, most of the information is on Meetup, and that's where you would sign up for our programs. We're affiliated with the National ACM. In fact, our last program on cinematic scientific visualization was just promoted to the ACM YouTube channel, which was a great honor on our part. And so we'll hopefully provide the link so you can see that, but you can search for that under the ACM YouTube channel. So without any further comments, let's turn it over to our chair, Alvin, on his presentation.
So actually, before that, before we start, I also want to kind of introduce as well Mid-America Club ITCONNECT. So if you're not familiar, in Chicago, Mid-America Club is a private business and social club. It's held on the 80th floor of the Aon Center. So if you've been to the Aon building, it's on the 80th floor. It has 360-degree panoramic views of the skyline. So we've had, if we were actually in person, we've had our meetings there. And in fact, actually, we had our last meeting, I believe it was in February, I think it was, before the lockdown or so, before the COVID. So we had our last meeting in February. And then also, it's similar to IEEE Computer Society, we do lots of monthly meetings on the same various topics too as well. So the chair is VJ, and I'm the vice chair, and you can see the credentials there if you want to know more information about the Mid-America ITCONNECT and the Mid-America Club as well. Okay, so yes, I'm going to ask now Kevin, if you can go ahead and do the introduction.
Sure. All right. So our speaker tonight is Alvin Chin. Alvin is a AI and emerging technology researcher at BMW Technology Corporation for his day job. For his night job, he heads up the majority of the IEEE committees in the Chicago area, as you have now heard. But he is also an adjunct professor at DePaul University, the chair for IEEE VTS Chicago, the Computer Society, and ACM. The publicity co-chair for IEEE the Vehicular Technology Conference fall of 2020. He's a member of IEEE and ACM, the secretary of IEEE Vehicle Technology Connected and Automated Vehicle Standards Committee, and he has worked over 12 years in research and innovation with Nokia research, Nokia, Microsoft, and BMW, and published over 30 publications and 10 patents. So thanks, Alvin, for putting this together and going through this talk tonight. I guess I will mention too at this point, if anybody does have any questions, please post them to the Q&A session, and we'll work through them at the end of the talk. Thanks.
Okay, great. Thank you, Kevin. Okay, so yes, I'm going to be talking about machine learning for the connected car. So this is actually work that I did with BMW Technology Corporation in Chicago. Previous work that I've done. So I'm going to kind of explain some of the 3 different types of use cases of machine learning for the connected car. So then the question you might ask yourself is that we have machine learning. Everybody knows when we think about vehicles, right? The first thing that comes to mind about machine learning is, well, self-driving cars, right? Using machine learning, using deep learning models to be able to detect, oh, this is a pedestrian, this is a traffic light, this is another car. So based upon that, the decision is to kind of brake and not go ahead or so. And we have some of those right now. So some of the ADAS systems or so out there with the different vehicle manufacturers have some level of recognition and machine learning, but not, obviously we haven't gotten into that fully automated state yet. But what I'm going to mention about for this talk is I'm going to talk about in terms of why we also need machine learning, not just for the self-driving automated vehicles, but also for connected vehicles. So you probably hear the term of CAV, which is connected and automated vehicles. Okay, so I'm going to talk about the connected vehicle side. So when we think about the connected vehicle, right, think about like your connected phone, right? So your phone has this connection, internet connection that connects to, different things, to internet, that connects to other phones, peer-to-peer, things like that. And so connected vehicles, you can think of it as like basically like, a phone that's moving around, right? So the connected vehicle space or so, the whole idea here is trying to bring this like digitalization into the vehicle. And we're beginning to see here that we have a lot of the enabling technologies that enable to do that now. So if you were to think about like 10 years ago, right, we didn't really have all these kind of pieces together, right? 10 years ago, cloud was not very, very, popular or so, right? Or big data for that matter. But now, we have cloud platforms, like Microsoft Azure, you have, Amazon Web Services, AWS. So it's very easy now to go ahead and pump data into the cloud. So there's where we get the information, and that's where the data can get stored into the cloud. So in terms of the vehicle can then go ahead and then send this data directly up to the cloud. The cloud can go ahead and do some big data and predictive analytics, and then create some particular types of intelligence or inference based upon that data through analytics and through machine learning, and then bring that back down to the vehicle to be able to operate. Or for example, it could also, let's say, learn when you should be leaving from home to go to work, and then tell you on your, let's say, your smartwatch that you should leave at this time in order to get to work. And that's actually some of the stuff that we had done as well in BMW, which I will go ahead and explain shortly. And then, of course, now you have the Internet of Things, right? So IoT, right? Because like a lot of these devices, like for example, we now have the smart home. So you have lots of devices like the Amazon Echo. So for example, in the case of for BMW, you can use the Echo to say, hey BMW, when should I leave for my next trip, right? And then it would then tell you that you should leave at this particular time, or say, hey BMW, how much fuel do I have remaining in the car? So something like that. Okay, so then, what are the reasons for having machine learning in the vehicle? So obviously I mentioned, autonomous driving is obviously, one of the important parts. But also as well, we also need it because we want to be able to improve, traffic and road safety, right? So we need to be able to determine, if another car is coming, or if you have another truck, or there's a bicycle or cyclist, we'd be able to do recognition of those particular types of objects. And also as well, integration with the smart city. So everybody's all talking about in terms of smart city sensors within like the traffic lights, things like that. And so we talk about, for example, vehicle to X. So in the automotive industry, there's something called V2X, which is basically vehicle to anything infrastructure. So it could be V2V, vehicle to vehicle, so like peer to peer. So two vehicles can communicate with each other, and then the other vehicle can make a decision based upon what the other vehicle sends. So then you could be able to have, in that essence, real-time traffic prediction, right? So think about, for example, if there is an accident that is on the I-90 that is about maybe several miles away or so, because another car was already there and witnessed it, it could then go ahead and communicate that to the vehicle behind it and so forth. And then from there, then then you yourself, the vehicle, as you're driving, then it would then say, oh, you know what, there's a traffic accident here, and so therefore you should be rerouted to another route or so. So that's with the smart city. But for this purposes of this talk, I'm going to talk about three applications of machine learning, which are journey management, predictive vehicle maintenance, and personal preferences. So let's first of all talk about journey management. So the idea here is that, we all take trips during the day. We go to different places. If you have a car, how do you go ahead and create intelligent management of these particular routes and trips that you do? So how do you kind of manage these particular types of journeys to make it easier for you? So for example, if you have a meeting you have to go to, you have to drive there. How can I be able to go ahead and it can then go directly to the car, and then I don't have to fiddle around and say, oh, you know what, how do I get to this particular place? It's already in the car. When I go into the car, boom, it pops up, and I can go directly to my destination. So this slide here, I like this kind of slide because it kind of like tells you kind of an overview in terms of what it is that in the life of a customer, right? What does the customer do on a daily basis, right? And how do we go ahead and approach and satisfy those individual mobility needs? So you think about a customer or you yourself, when you're driving, what do you need to do, right? You need to, first of all, you leave your home, you go to work, you have to find a place to park, you have to fill up gas, you have maybe some specific radio stations or satellite stations or music that you enjoy. You need to determine based upon the weather, whether, for example, you should have the let's say the sunroof, would be open or closed, because if it's raining, obviously you don't want to have the sunroof, open. Traffic, prediction, traffic particular patterns. So you can see here you have all these particular things that are happening throughout the day. And so how do we go ahead and kind of like digitalize that in a fashion that we can be able to go ahead and improve the user and the car experience. So the whole idea is like basically improving the experience of the user when they are driving, in the car, and to prepare them when they approach into the car that they have all the information that's necessary for them to go ahead and drive. Okay, and so with that, along that theme, BMW Technology Corporation in Chicago, we actually launched about 4 years ago, 2016, a service, an app called BMW Connected. So for some of you that have attended one of my previous talks before, I've mentioned about this many times. But for those people that don't know, this is our app and service that we had created to basically do that, to do this type of journey management. So based upon your scheduled appointments, it would then tell you that, oh, you should go ahead and leave for that scheduled appointment, and how to get there. Okay. But with that, actually, we are retiring BMW Connected because we're now upgrading it with what's called My BMW app. Okay, so the My BMW app, if any of you have a BMW and have used the BMW Connected app, it will be updated with this new one called My BMW app. And so basically, I like this kind of like, one phrase. It connects your vehicle to your life, right? Because everything that you're doing in the vehicle revolves around what you're doing every day in your life. And how do you take those particular events and those particular stuff that you're doing and put it into the vehicle? Because the vehicle is part of your lifestyle. Okay, so that's the My BMW app. Actually, right now it is available in Europe and Asia markets, but not yet for the North American market. But it will be available soon. So I'm going to talk about now in terms of what we did in terms of machine learning for the BMW Connected app. So if you had the Connected app and you have it still running on your BMW, I'm going to kind of show you in terms of like what exactly is happening in the back end, in the hoods. So basically, with BMW Connected, the ultimate thing we're trying to do is that we want to use machine learning to learn customers' driving behavior patterns. Basically, that's what it is in a nutshell. But in order to do that, we need to first of all learn where they go, right? So we have to learn their destinations, and that's the fundamental part of the machine learning part in terms of for BMW Connected is learning those destinations. So how do we do that? So you might be familiar with the concept of clustering. Okay, so basically what it's trying to do is that we are collecting data in a vehicle when you start the car and then when you approach a destination. So we collect all these vehicle points, these GPS locations. When you park your car, okay, we also get a bunch of other GPS locations. So you can see here, if you can see my cursor here, right? So you can see here is that you might have different types of location points, right? Because as we know with GPS, it's not always very accurate. It's not going to be always in the same location. The whole idea here is to determine where you are at is to kind of cluster, figure out the ones that are similar to each other or close to each other. That's the concept of clustering, and be able to kind of predict to say, okay, based upon these particular points, I think you were here. And the way we do that is that once we find this cluster, then we can find the center of that cluster. Once we find the center of that cluster, we know then what that GPS, the latitude longitude is, and then we can then go ahead and do a reverse lookup and say, okay, that latitude longitude refers to this particular address. So for example, in this example here, this is referring to 14 West Superior Street. And if you're familiar with where that is, basically that is Holy Name Cathedral, which is a church in downtown Chicago. So basically, based upon from the latitude longitude of the center of the cluster, then we can go ahead and make a call to, let's say, for example, to here, API or Google API, Maps API to determine, what is the actual point of interest. In this case, it is Holy Name Cathedral. And you can see here, these are also the other, types of destinations that I automatically learned while I was driving. Okay, so in terms of, the algorithm that we do for learning these destinations, so the thing you have to consider too as well is that, we don't want to also identify particular locations where, let's say, you only just stayed only for, let's say, a couple of seconds or a minute. Like, for example, let's say that, you are driving from home to work, but you had to go to the washroom. So you stopped at a gas station to go to the washroom and then come back, right? Well, we don't want to learn that particular gas station as part of a destination, because that was just kind of a pit stop, right? So what we do here is that we identify what's called stay points. So what the stay point means is that you have to be at a particular location and stay there for a certain period of time for us to detect, to say that, oh yes, you know what, you actually were there, so we'll call that an actual destination. So in our case, we use something like 10 minutes, right? Of course, this is a parameter, so it can be configurable or so. But in our case, we use 10 minutes. So you have to be 10 minutes at a particular place there in order to actually identify it as a stay point. And then from those particular stay points, then we use what's called hierarchical clustering to be able to go ahead and to say that, for example, this is a particular place that you were at, and this is, let's say, home, and this is a particular thing called work. So we actually identify through the BMW Connected app where your home is and where your work is based upon the spatial and temporal patterns. Okay, and then with that, once we have those learned destinations, then we know what are your frequent destinations, right? And then we know that, for example, every day from home to work, every day, let's say at around 7 a.m. or so, you drive your car from home to work. So this is where we have the predicted trip algorithm that goes ahead and does that. So first of all, it has to be a frequent trip. And then we do this trip data processing here. So we identify the trip segment, the trip end detection. We do stay point clustering, and we determine whether it is from home to work, or let's say home to the gym. We do then predictive modeling. So we determine your destination arrival behavior patterns. What is your estimated time of arrival? What is the stay duration modeling? And the departure behavior learned from the data. And then from there, we kind of combine this together, and we kind of predict a departure time. And so we use this contextual association rule mining. So if you're familiar with data mining techniques or so, this is a particular rule mining algorithm that basically is trying to find frequent co-occurring associations. So for example, based upon the context, it may determine to say that, okay, this is Monday, and from 6:30 to 7, around that time, you go from home to the railway station. Yeah, I'll answer the questions afterwards during the Q&A. And anyway, so in terms of for the so once we learn the frequent and predicted trips, then we can go ahead and then put that into the connected app. So then you can see here that once we learn that, then it shows as the interface. So in this case here, we have a notification that says you need to leave in 10 minutes to get to a driverless city. So it takes into account, what is your predicted departure time, but also in terms of the traffic situation that's happening right now. Okay. And then on the second screenshot here, you can see that these are the list of particular trips that you're going to be going to. And then it also has a trip summary. So from here, if you're driving, let's say in my case here, I drove from Schaumburg to Chicago, then it could go ahead and give me my summary of that particular trip in terms of how long it took me and what was the average speed, and in terms of also how much fuel that I used. And then what's really nice about this is that once you have a particular location or so, then you can easily go ahead and send it to the vehicles, right? So no more having to fiddle around in the car to set the destination, right? You can just go ahead, let's say in advance of, let's say if I'm taking a trip, let's say to go to Boston or whatever. And then the thing is that then I can be able to go ahead and find, let's say on the Apple Maps, where's the place in Boston. Let's say I have a favorite seafood place, Legal Seafoods. I can then enter that into the Apple Maps, and then from there I can go ahead and then send that directly to BMW Connected, which will then go ahead and send it to the vehicle. So when I go into the vehicle, it pops up and I can be able to go ahead up to Boston, for example. Okay, and then here's an example where, for example, I actually gave a talk, the ultimate smart driving machine powering the connected car with machine learning. And then based upon that, you can see here on the app, it says you can go. So if you're in the car, it will then connect to the car, and then you can go directly. Or if you're out of the car, then you can send a message to the vehicle, and in the vehicle, you can go ahead and enter in. And then it tells me that I should leave in 15 minutes to get to the ultimate smart driving machine. And then when I approach the vehicle, then I get this pop-up right away that says my next trip is to go to this particular place or so, which in this case actually was the office, 540 West Madison in that case. But anyway, you see the idea here, right? So you're basically we're creating this end-to-end platform that based upon a particular location or based on the particular trip, or based upon some calendar entry that you have, then we can then go ahead and take that from the phone and then go directly to put it into the car. Okay, and like I mentioned earlier, in terms of learning the fuel consumption from the trip summary, then you can see here in the case for the Schaumburg to Chicago, you can see here that I left at 9:22, arrived Chicago at 10:02, 40-minute trip time, 28 miles distance, the average speed, and the fuel used. Now the thing is that the issue is that with the fuel used is that if you look at it from the car's point of view, it's not exactly always correct, right? Because it depends on how fast you're driving, different type of environmental parameters. If you're, let's say, on a hill or whatever, so the gauge in terms of your gas tank level or so, it's not going to be always very accurate. Okay, so the car actually does some type of kind of approximation or so. So it's not always very accurate in terms of how much gas you might have remaining in the car. So then what we did here is that we said, okay, well then let's go ahead and let's use machine learning. In this case here, we use this kind of Gaussian function to try to determine, what is the actual fuel consumption that you took from that trip summary. So we had some particular data points, and then we just, based upon the data points, we fitted it to a Gaussian function. We had the equation kind of based on here, and then implemented it. So based upon what is your travel speed, then it would go ahead and calculate what is your fuel consumption rate. Okay, so that's the first part, which is on the journey management. Yeah. Okay. So the next part I'm going to talk about is the vehicle predictive vehicle maintenance. Okay. So this is basically trying to predict when a particular part in the vehicle may particular fail, and so therefore you should take it into service, let's say, or look at it before it actually becomes an actual failure. Okay, so this work was actually presented last year's VTC conference, which was actually in person. So it was actually in Honolulu, in Hawaii. Wish I was there now. But anyway, that being said, so this is work that I did together with Peter Wolf and Jalei Tian, our previous colleagues. And we basically did a work here on trying to use cloud and IoT edge to be able to create an efficient data-driven automotive diagnostics. So the background here is that, we want to be able to detect early faults, before they become failures, right? So you don't want to get to a point where, oh, okay, then I have to, schedule an appointment with going to the dealership to do service. If it could tell me way in advance, so I don't have to replace a particular part, it's going to cost me how much to replace a particular part. All right. And so basically, in this particular area, there are approaches to detect faults. So for example, there are rule-based approaches, there are model-based approaches. But however, the problem is that with now, the vehicle has so much data that's being pumped through. So for example, in the case of BMW Connected, we get vehicle data, on the orders of gigabytes, per second or so. So, how do you, first of all, how do you kind of like process that data? And also, of course, the complexity of the vehicle now in terms of its components. Okay, so we can perform data-driven automotive diagnostics with machine learning and deep learning, but usually that is, done, off-board and it's not automated. So for the example that I'm going to illustrate here, I'm going to show, how we can use machine learning to detect pre-ignitions before they cause a serious material damage to the engine of the car. So if you're familiar or not with a pre-ignition, right? So you know that when you start the car, so right, you have this kind of spark timing before the engine starts. But sometimes you have something called pre-ignition, so before the ignition starts. So what happens is that, it is a combustion. So what pre-ignition is that it's a combustion of the fuel-air mixture in a cylinder that is not triggered by a spark, but a hot spot. And these things actually do occur. And the problem is that, if you ignore this for too many times or so, then it could cause serious damage to your car. So of course, then our main aim is to suppress these pre-ignitions. Okay, so that's the context. In terms of what my previous colleague Peter Wolf did before, is that he created this machine learning, actually a deep learning model, which he called the deep diagnostics model, that basically took all the particular signals from the ECUs. So that's the electrical control units that are in the car. And then from there, he was able to use a deep learning algorithm that took those particular features using CNN and LSTM. And I'll go ahead and explain briefly what those are. And by creating that algorithm, he was able to go ahead and create this model to then predict whether there was a pre-ignition or there would not be a pre-ignition. Okay, but this was all done, his experiments here was all done on an actual computer. Okay, and so the thing is that, if you want to now create this model and you want to, let's say, deploy it to a fleet of vehicles, then how do you do that, right? So this is what this paper was trying to address, is that how do we go ahead and create this end-to-end kind of, if you're doing it for many fleets of vehicles, how do you go ahead and, let's say, you could just upload the model, directly remote, let's say remote software update, right, for the vehicle. Okay, so I'm going to talk about briefly. So CNN is not the not cable news network. It's a convolutional neural network. So you might have heard of this in the machine learning for deep learning. And so basically, a lot of the deep learning models use convolutional neural network. So basically, that kind of the whole idea here is that you have an input. In this case here, let's say it's an image of a car. So, and based upon all these particular data points, you do this kind of feature learning on that. So you're trying to learn particular features of this particular car. And then once you get those particular features, then you do a classification. And then from the classification, then you can then determine through the different layered architecture, whether, let's say, this is a car or this is a truck or a van or a bicycle, for example. Okay. And basically, a convolutional neural network is kind of like based upon, think about, you in your brain, right? You have neurons, right? So how does the neuron process, information or so? So basically, it's creating this kind of a simulation of a neural kind of network that you have, for the brain. And then in addition as well, we have something called LSTM, which is called long short-term memory. Basically, this is like a component or so that adds the memory element or so. So you have an input, xt. And then what happens is that you have an input gate and a forget gate and an output gate, depending on the different, the gates opening and closing, then you can be able to, let's say, store, some particular type of memory. So this is kind of the memory unit or so for the deep learning model. Okay, so what happens there is that you can now create a deep learning model that has many different combinations of convolutional neural networks, as well as long short-term memory. Okay, so you can have different combinations, and different combinations will yield different results in terms of the prediction accuracy. So that's actually what was done with that. And actually, we kind of found out was that if we use the combination of 4 CNNs and 2 LSTMs, that actually was the best accuracy to give us for the pre-ignition detection. Okay, so that was what we had discovered, but obviously, like I mentioned earlier, the problem in this paper was basically looking at how do you run the model in the car when you have resources that are constrained. Okay, so the thing is that you don't have access to like a big machine or clusters or whatever, right? So the thing is that you want to run it in the car, and you only have limited resources, computing resources in the car. So how do you go ahead and do that? And then second of all, if you're going to go ahead and do the development and management and deployment to thousands of cars, how do you do that easily? So that was kind of what we wanted to tackle once we have the model. So then what we did here in terms of our contributions is that we created an end-to-end framework using enterprise cloud and IoT edge technologies, and we used that for training, testing, and deploying. And then we evaluated our model with other particular models that varied the number of CNNs and LSTMs. Okay, so here this kind of shows you kind of what we did overall here. This is our framework. So basically what you have here on the left side here is you have, this is being done on the local machine. So first of all, you create your model. And then after you create your model, then you go ahead and you put it to the cloud. And then from that model, you can go ahead and do training. And in the cloud, obviously, you can be able to run as many experiments that you want to do, right? So that's the advantage of having a cloud platform. So we go ahead and do that. But also as well, we also have to create an IoT edge module, right? So we want to run it on an embedded device. So we have to package it into a container or so. And that's actually where once we create the code there, then the cloud will go ahead and take that, and then we'll make it containerized, like for example, using a Docker image or so. And then after that, then we have what's called an IoT hub that kind of like maintains, all these, Docker images or so, and then you can go ahead and deploy them directly, send them directly to this IoT edge device. So the IoT edge device needs to run a runtime module, so an IoT edge runtime. And then you have the modules. So we have the scoring model. And then here we have the pre-ignition data source, because since we just had a bunch of data in order to kind of like simulate that this is coming in real time, so we had to create kind of a stream of data. So basically what we did is that we took this kind of data source and we kind of did it in a loop to pretend that you have this data feeding in, and then in real time it would then go ahead and do the scoring to say yes, pre-ignition or not pre-ignition. Okay, so our pre-ignition data set, we used 1,600 plus test drives with a special gasoline to actually have some type of pre-ignitions. So in this case here, what we found out is that it was a high dimensional data, so there was 1,681 features from those ECU signals. We used hypothesis testing to identify 484 statistically relevant features. And then from there, obviously, if you use all those particular features, you're gonna, have a very, very complicated model. It's gonna take a long time to run. So then what we decided to do is that we just go ahead and do the top 50% of those 484. So that gave us 242 features. And we tried out, maybe we don't need all those particular features, right? So if we go ahead and rate them, then maybe we could just take the top 5%, which is only 24 features. That might be good enough to give us a very good, accurate model. Okay, and then we split the data set, 70% training data, 15% validation, and 15% test data. Okay, in terms of development and implementation, in order to run this as an IoT edge device or so, we were simulation, so we didn't actually run it within a vehicle, but we pretended if it was a particular vehicle that had some particular module running or so, how would it look like? So we just used like a Raspberry Pi 3 Plus to kind of simulate this. because it's a constrained environment, right? So we wanted to see, you know, how the performance is. So we trained the models using Python, and we use Microsoft Azure platform. So Microsoft Azure has a machine learning service. AWS is something, you know, similar with SageMaker. And then we executed the predictive models using Python, Docker, and Azure IoT Edge. And then we visualized the results using Microsoft Power BI to see how accurate, whether it was a pre-ignition or not pre-ignition. So in here, you can see here, these are all the different models that we kind of tried out, right? So you can see here that the one that we said was the one that we had used was 4 CNN and 2 LSTM because that gave us the highest accuracy score. So F1 is used in machine learning or so to measure accuracy. So of course, the higher number, then the more prediction, the better prediction accuracy this is. So if you look at all the particular models here, then you would say that, oh, 89.3% for CNN 2 LSTM is the best. Okay, but the thing is that you see the other ones don't really much different, right, in terms of the difference. And also as well, you can see that other ones, you know, are more complicated, right? So 6 CNNs might be more complicated network model than 4 CNNs, and of course, 1 CNN is less complicated. Okay, so the whole idea here is that, you know, you may think that your intuition might say that, you know what, the highest accuracy, I should go ahead and deploy that model. But no, that's not necessarily the case. Because the thing is that maybe this particular model might take a very long time. You might use a simpler model, sacrifice the accuracy a little bit, but not too much, and it would actually perform better. And that's exactly what we did, right? So that's where this slide shows in terms of performance results. So the base case here that we use is LDA and logistic regression. So you can see here it performed worse in terms of F1 score, only 69%. But you see here that when we actually ran the experiments on the Raspberry Pi, and of course we did several experiments and then we took the mean of it, we found out in terms of how long it took to predict the pre-ignition or not pre-ignition, it took 12.4 milliseconds versus that if you were to run it using 4 CNN and 2 LSTM, which gave us the highest accuracy, that would have given us 104 milliseconds, right? So obviously, you know, when you're thinking about running these models in the car, you need to have efficiency, but you also need to have it such that it's fast too as well, right? And so the thing is that you might be able to, let's say, sacrifice a little bit of accuracy, but you would get a much better, you know, performance. Okay, so this is an example. You can see here that one here that's in green, 1 CNN and 0 LSTM, you know, compared to 89.3%, this is 87.2%, but then this gives us the fastest performance, 22.7 milliseconds. And then you can see here from Power BI, we actually, you know, put the streaming data that we got from the Raspberry Pi, and then we got the truth. So that's the actual, you know, data value that we got from the data set, and then what's the predicted based upon our model. And you can see for the most part, you know, it pretty much kind of follows pretty good. So that was done in the Microsoft Power BI. Okay, and my last part is going to be talking about personal preferences, right? So obviously now, you know, we talk about connected cars and automated cars, we want to have personalization in the vehicle. So this is work that we actually presented this year in the VTC 2020 fall, which is a virtual conference now, which is until December the 16th. So like I said earlier, you know, if you want to register for that, you can see my talk that I did over there. But I'll also talk a little bit briefly here as well. So basically the whole idea here was trying to predict predictive preconditioning. Okay, so let me give you some background, right? So in terms of personalization in the vehicle, you know, we do actually have personalization, but the problem is that it's explicit, right? So in the case of, for example, if you want to, you know, set, you know, the fan or so in the car, so you have to manually say, I want to schedule ventilation, and then I want to send the departure time as to when I want to do the ventilation, or when I want to schedule heating or cooling if you have an electric car. Also, in the case here for BMW, and I'm sure of other vehicles as well, you can also set, for example, for the driver, you know, what is the level of seat heating that you want, and when do you want seat heating to occur. But this is kind of rule-based, right? Because the thing is that this is absolute, right? So if it's automatically below 50 degrees Fahrenheit, you're going to do it, right? But for another person, it might be different, and you have to explicitly specify that. So actually what we want to do here is that we want to be able to kind of learn from your previous behavior, what you did before, learn that, and then automatically then set that for you. So you don't have to actually set it, you know, yourself or so. Okay, so that's the whole idea here regarding about this predictive preconditioning, is that I want to be able to predict when I'm going to go on my next trip and make sure that the vehicle is comfortable enough for me to be able to drive off. So there's previous work in this. So there's some like patents or so from GM that deal with like, how you can automatically wake up the vehicle and then you perform preconditioning before the requested departure time. There's lots of stuff in terms of infotainment, recommending personalized audio content, personalized, ADAS. And we actually presented in 2018 in the Vehicle Technology Conference, how we can automatically learn seat heating preferences using an individualized learning model. So what we wanted to do here is that, how can we create a system for a personalized smart interior that can provide a proactive and a comfortable user experience? And then, in addition, for the predictive preconditioning, how can we recommend and notify drivers, when to precondition their vehicles, depending on certain types of environmental context. So the vehicle's parking environment, the user behavior, departure time, and the weather. Okay, so in terms of our solution and contributions here, so we created a machine learning framework for the smart interior, and we created kind of notifications to let drivers know that when they should be leaving and whether they should precondition their car beforehand. And we actually implemented this. So we actually did it in a production environment in BMW Connected that actually we had about 2 years ago or so. So we actually did implement it, and we actually got some results of people using it. And then we evaluated the performance and the effectiveness of our algorithm in terms of also user feedback too as well, to see whether people actually did accept the notification and to start the preconditioning. So this is kind of the flow of what I mean by predictive preconditioning. So the idea here is that you start your vehicle when you're parked, and then what happens is that then we see whether, are you going to be predicted departure or not? If it's yes, then we go to the smart preconditioning model. We get the current weather, and from there we can determine, based upon your previous or so your behavior patterns, whether there's a need to precondition. So for example, if you're a person that always will set up the heat when it's less than 35 Fahrenheit or so, then when the temperature becomes 35 Fahrenheit, then it will automatically tell you, do you want to heat up the car? Okay, and then if you want to heat up the car, then if it's a yes, then it sends a notification to you for the BMW Connected app. You receive that notification, and then you can go ahead and then it will go ahead and precondition the vehicle. Okay, so that's the kind of the flow for that. This is what it looks like. So in terms of the app, what will happen is that you will get this kind of a tile here that says predictive preconditioning. So in this case here, I had a BMW X1, and I was going to United Center or so, and it's telling me that I should go ahead and start predictive preconditioning. Okay, so that's the UX part. All right, so in terms of actually the model itself, so basically what we're doing here is that first of all, we collect the personal driving data. So we collect the location data, what's the exterior temperature, what's the interior temperature in the car, and what's the current weather temperature. And then from there, we create a global model where we do a feature extraction. So we took the exterior temperature, we determined what's the wait time. So that's the duration between the first car data record. Oops, went too fast there. So we determined the wait time, the duration between the first car record and the first record where we get the actual temperature recorded. And why we do that is that we want to determine, whether you're actually maybe, in an indoor or whether you were outdoor, right? Because there's going to be a difference in temperature. So we get the maximum difference between interior temperature and exterior temperature. And then from there, we calculate this function where we can calculate the outdoor parking probability. And then based upon that, we create this global comfortable temperature model based upon all the various users that have the data. And then after that, we combine that together to create this global preconditioning model. And we use supervised learning to learn the relationship between preconditioning, the exterior temperature, and the wait time. So in the interest of time, I'm going to kind of speed up here so we have time for questions. Okay, so next slide. Okay, so basically what we did here is that we created a biologistic regression model. We find the personalized parameters and we optimize it. And then after we created this personalized preconditioning model, then we get the preconditioning decision and we get the user feedback, right? So we look at the preconditioning model and look at whether the person did the preconditioning or not, and then we use that as feedback to be able to go ahead and improve the model. And then here's the algorithm evaluation. So in this case here, we used 240 trips, and we can see here these are the data points in terms of what was the exterior temperature and what was the interior temperature, and whether they would do preconditioning or not. And so based upon the model, then you can see here that based upon this is in degrees Celsius, you can see that, okay, when it's like, less than, 10 degrees Celsius or so, for the majority of the parts, preconditioning is 1, which means that there is preconditioning, and 0 is no preconditioning. So you got to remember here, this was done using data that was in Europe. So we used the European vehicle data for this. And so from here, we got an accuracy of about 91%, precision about 76%, and recall about 89%. Okay, and then with that, we wanted to then compare or look at the system performance and the analytics. So the thing is that, once the users get the notification that they have preconditioning, then we wanted to see, okay, what was actually sent versus the actual exterior temperature. So you can see here that in orange, this is like the number of heating preconditioning notifications. So you can see for the most part, if it's like between like something like minus, let's say 6 to like 12 degrees Celsius, for the most part, people, do get heating preconditioning. So for most users, they will want that. Actually, we find out actually in Europe, a lot of customers, even if it's like 12 degrees Celsius or so, they do want to have heat preconditioning. Whereas maybe here for us, we can, bear with having, that type of temperature. And then for the gray part, you can see here's the number of cooling, preconditioning notifications to see, match the expectations versus the reality. And then we found out that an active user, on average, executed cooling, heating, or ventilation at least twice in a week. So it seemed to be that, people did actually, did have those notifications pop up, which means that they were actively using the system. Okay, so basically, yes, so this is coming to my end or so. So basically, in summary, what I want to say is that, machine learning can be used to learn driver behavior patterns. So you saw that in terms of for learning home, for learning work, for predicted trips. So that's for journey management. So that's the first part. And then the second part is that we can use machine learning to predict faults for the components before they become failures. And we saw that with the pre-ignition. So that's for predictive maintenance. And then the last application that I showed about is that how machine learning can be used to learn a user's personal preferences for personalization in the vehicle. So in this case here, this is the predictive preconditioning. And ultimately, of course, machine learning can be used to make the ultimate smart driving machine. At least that is the what we want to do. Okay, and with that, questions?
Alvin, thank you very much first off for that really interesting presentation. That was pretty cool. I'll have to look up those papers. We do have a considerable amount of questions, and I think more are still coming in. So I guess we'll get started with this. Feel free to stick around, I guess, to everyone as long as you can. And Alvin will let us know when I guess things are going to be coming to an end on his side. So first off, have you received feedback from customers with regards to the accuracy of the fuel consumption predictions?
The accuracy. So we had a lot of feedback to say that they actually did like the feature because it did tell them, oh, in terms of like, do I need to improve my, driving capability or so. But in terms of accuracy, no, I didn't really see too much on that.
Okay. I think Mark and I were going to be bouncing back and forth on some of these questions too. So I'll jump on to the next one that we've got listed here.
Yeah, and also before you go to the next question, I have a poll up and running. So if you need to, leave or so, if you can complete the poll to kind of give us some feedback on the webinar, that'd be great.
Great, thanks. Okay, so are the stay points based on where the vehicle goes or where the cell phone in the pocket goes?
Ah, yes, good question, good question. So actually, in our case, it's actually both. So actually, what I neglected to mention is that besides collecting the data in the car, we also do collect phone data that is out of the car. So the thing is that you can override that. So the thing is that there's permissions in the BMW Connected app that say that, share or collect my location, while using the app or while the app is in the background, or do not collect the phone location data.
Interesting.
Okay, we have another question here. Did the remaining features for pre-ignition failures give you an idea of what's causing those firings?
The remaining, no, we didn't really kind of like explore that into that level of detail. It was just more of like trying to determine whether it was just pre-ignition or no pre-ignition. So we didn't really actually look in terms of the detailed part of it. So the answer is no, we didn't.
Okay. All right. Let's see. Will the maintenance systems proactively communicate with approved BMW technicians so that the drivers don't ignore required repair and recall work?
Yeah. So I mean, the thing is that you have to think about here, or you have to kind of take into consideration that this was just like kind of a research type of work, right? So the thing is that this wasn't really something that actually was deployed or put into production yet. So this is just kind of like letting other BMW kind of like entities, kind of knows that, what, have you considered, perhaps using, machine learning to be able to detect these particular types of, faults. And actually, I do know that, in a lot of BMW plants or so, they are now beginning to use, AI and machine learning models for doing this. So.
Okay, next question is, how does this work relate to the Illinois tollways creating one of the nation's most sophisticated smart highway systems?
Yeah, good question. Yeah, so I think to answer that question is that, yeah, so I think it's that, for the BMW system or so, I mean, obviously, we are collecting stuff for our own particular types of purposes for the BMW connected, for our particular features or so. I know there's like some work which is dealing with, vehicle to X technology in terms of like, so that's actually there's actually a consortium for doing this vehicle to X kind of a platform to be able to kind of have vehicles to communicate to the cloud, vehicles to communicate to each other. So that's actually in the works right now. So I would say that particular part would probably be more connected towards the smart highway system.
All right. So do you see any benefits to app capabilities from the or drawbacks, I guess, from that standpoint, from the recent FCC directive moving from DSRC to CV2X?
Yeah. There's that debate between DSRC to CV2X. That's right. Yeah, I mean, so I think the thing is that with DSRC, I mean, there was a lot of promise for that, but I think the CV2X is playing a huge part now because there's lots of there's like an entire consortium now around this. There's lots of momentum around this. A lot of players, even BMW, is part of that consortium too as well. And also as well, it's using 5G technology, right? It's using the 5G cellular peer-to-peer. So I think it's just in terms of architecture, I think probably it is more easier and I think for interoperability too as well, right? Because you need to have interoperability as well. So
yeah.
That's what I would say, yeah. Okay, there's a question here. I see that. Okay. Oh, okay. Regarding about understanding how you select which of these concepts are new and valuable, and then send them to BMW legal to consider for patenting. As an avid inventor, has your experience been that these types of inventions are valued by BMW for patenting or not worth the extra work? Yeah, that's a very, very, very good question on that. So I would say that some of these particular stuff that we did, like for example, the collecting, of the data. So when I mentioned about collecting the data, right? One of the issues is that because you're collecting data from the phone too as well, and sometimes people do not have their phone charged when they're in the car or connected to USB for that matter. So it's going to drain the battery. So we did have a patent that we created to kind of like help to address that. So we get to a point where like if you're driving in the car, you don't get to the point where you go to your destination and you only have like 20% battery remaining or so, right? So we did do a kind of a patent for that. Yeah, so the thing is that, when we do have particular patents, obviously, we do send them to BMW legal. And in terms of worth BMW so in terms of these types of inventions are valued by BMW for patenting. I think it really depends. I think, for BMW, I think BMW, values, certain patents, obviously, for sure, because in terms of for innovation. So that's, where I'm now in the team now where we're dealing with, AI and innovation, and how do we able to kind of protect our innovations through particular patents. And actually, another thing I will say is that the predictive preconditioning that I presented was actually based upon a patent that we had submitted. So.
Interesting. Thanks. Okay, so are you leveraging existing contextual awareness frameworks for machine learning?
Existing contextual environment frameworks.
Existing contextual awareness frameworks.
Oh, awareness. Existing contextual awareness. Yeah. So the machine learning that we are doing is that, so for the phone, we're primarily using location data. In terms of for the vehicle, we use, temperature data. We used, what else do we use? Yeah, we primarily use like, the temperature data, and we use we have seat heating data, we have location data. But the phone was just basically kind of location. I actually did a pet project to kind of see, whether we could use like, accelerometer, right, and gyroscope, try to determine the actual activity that you're doing. So when you leave the car, you're actually maybe, walking to the next destination. Because one of the issues that we kind of found out that when we were learning destinations is that, what happens if you actually park the car at this particular place, but actually you're walking, certain distance to get to the next destination, right? And your next destination, where you actually go. So for example, if you're parking, let's say, your vehicle to the work, maybe you have to walk, 5 minutes or so to get to the office. But because you have only vehicle data, then it's only telling you that you actually parked there, what actually you actually were in a particular building, right? So this is kind of where we had thought about in that transition period between in the vehicle and out of the vehicle. If we were to determine and know that you were out of the vehicle and that actually you were actually walking as the activity, then we could go ahead and then determine, oh, okay, your actual POI, your actual location or so is actually not where the vehicle was parked, but actually, let's say in the office.
Okay, next question is, my auto insurer wants to track my trips on their own app.
Yeah.
Is there an effort to allow insurers access to my BMW app to get the same information that would affect any rates and rebates?
Yeah, good question. So I don't know too much in regards about this area, but I know that there has been discussion in terms of how to work with insurers and in terms of how they would be able to get the data. Obviously, there's some there's data issues in terms of what type of data in terms of privacy, right? Because BMW really takes privacy very seriously, right? So when you install the app, you have to first of all agree to all these legal conditions or so. And users, if they don't want to, they can go ahead and remove the app and request that they don't want to have data, collected or so. So that's a very tricky question. But I think we're trying to get more people around being able to have access to maybe through APIs, let's say, for example, right, to be able to use that.
You did have one request if you could slow your, or if you could show your slide about the framework of journey management, and then I've got another question after you get to that too.
Okay, slide of journey management.
That might have been pretty early on, right?
Yeah. Let me just go. Sorry.
Let's see.
So it's not this one. This one here.
Guess so. I'm not quite sure. I just saw that pop up. Yeah, the framework of journey management. So that looks like that might be it.
Okay.
Another question that was here was, did the data vary once individuals became aware of what type of data is being collected? That have any impact?
Did the what? Sorry, I didn't get the first part. Did
the data vary once individuals
the data
became?
vary.
Yeah.
I'm not quite sure I understand that kind of what the question is asking. You mean, do people change their behavior? You mean? Or?
Yep. Yeah, I think that's what they're getting at is once people became aware of what data was maybe being captured and how it was
Oh,
being
I see.
used,
I
and
see.
maybe
I
how
see.
did it have any impact on their use, I guess, of the system.
Right, right. I think for the most part, not really, because I think a lot of people, they knew that data was being collected, but then they just used the app and then they see all these particular things that show up, or so they didn't really have, any particular, you know, yeah, any particular, thing to say that, oh, you know what, that, that you did something, but actually, what I will say that there were some customers that were, maybe complaining to say that, okay, you learned my home here, but actually I wasn't really home here because I moved to another, or I'm like a nomad or so, right? So I'm on like remote work, so don't really have an actual, for example, work, let's say not home, but work, right? That I actually worked at different places or different locations. So there were some, people that kind of said that, no, this is not my work location or so. And then of course we had to get permission from them to look at their data and to determine, why that was the particular case or not. But for the most part, people pretty much do, regular. I mean, you would be surprised to see that, people usually have regular driving patterns, right? For the most part. I mean, obviously, of course, you can't predict so much during the weekend because people do different things over the weekend per se. But in terms of like, going from home to work, on a daily basis, it's been pretty good. And we calculated the prediction accuracy, and it seems to be that, that it's not, it does quite well. So.
Here's another question. Personalization features seem targeted at a single user, in other words, the driver.
Yep.
We frequently have passengers in our cars.
Sure,
How can
sure,
the system account for that?
Yeah, definitely. I mean, this is an example for driver, but passenger can also be done too, right? So it's just a matter of getting, getting the data from the passenger. So for example, the passenger, is what the passenger selects or so in terms of their climate control settings, or let's say for the seat heating or what have you. So yeah, definitely. I mean, once we have the passenger data, we can also do things similar to as well. Okay, and I think one final question.
Yeah, I think just as a quick follow-up to the request for the journey management slide, I think somebody was looking at page 11 is what they were looking at instead of page 6.
Let me see page 11 here. Let me go to here.
Yeah.
Just predicted trips.
Maybe. Yeah, I'm not quite sure. Another question that did come in too is, and I guess this might be the final question that we'll ask is, how do you push the new machine learning models to the car, and how is it connected to the network?
Yeah, so the thing is that in the work that we did, we didn't actually push it to the car, right? So in the case of for the pre-ignition, it was more of like, just simulating that capability to see, if we were to do that, how would the performance be? Because in that case, we didn't really have access to a car that could, actually, do that per se, at least during the time period when we were doing it. So the thing is that's why we use, simulation to kind of like see, how it is, and if that particular environment was simulated to, let's say, to a vehicle, that's the next step, right? The next step would be to go ahead and actually try to implement that into, let's say, one of the, vehicle simulators that we have or so to see, how that would perform. But we don't have anything in terms of actually like, putting it within in the actual vehicle per se. So this was kind of more of an exploratory research project.
Yeah. Okay. Let's see. We have made it through most of the questions. There might be a few more that are listed in here. Is it about time to close out, or do you have anything else to mention here, Alvin?
Yeah. So I think in the interest of time or so, we are now 7:11 or so. So let's go ahead and I think wrap it up. So let me go ahead and go back to the to this, and I think Mark can go ahead and now talk about our next webinars that we have. So Mark,
and
go ahead.
There was a question about PDH or professional engineering
yes.
continuing education hours too. So
yes. So after this webinar, those people that have attended or have registered will receive an email that will contain the recording to this webinar, the slides for the webinar, as well as a link where you can get your PDH certificate. So you can just enter your name there, and you can use that.
Great.
Okay,
so here we go. So we have 2 in January, and go ahead.
right. Okay. So one moment. So our first presentation. Notice this is different. Our meeting is at 11 a.m. Central Time because our speaker is in Europe, and that is David Heinemeier Hansen, who is the creator of Ruby on Rails and also involved with Basecamp. And he's going to be speaking on all things web development, such as the 2021 Majestic Monolith, Jamstack apps, and progressive web apps. And there'll be more information on our meetup site. So don't miss this event. And 1 week afterwards, we're going to have a special speaker, repeat speaker for the ACM, Dr. Mark Bennett of NVIDIA. And he's going to be speaking about explaining and accelerating machine learning for finance, where machine learning can extract deep, complex insights out of large decision trees using shapely values to create advanced models which deliver real business value through significantly improving on traditional regression models. And he's going to show how AI techniques like will take to the extreme feeding data through multiple nonlinear tensor transformation, millions of parameters, and simplifying these explanations using classifiers like extreme gradient boosting using Python, sklearn, and notebooks. So Mark's a really learned person, great speaker, great guy. I hope you all can come and see this presentation. And there's a paper attached to our meetup, so you can read all about this. So thanks for attending tonight, and hope to see you in our future events. And don't forget, we're always looking for new speakers. That could be you.
Yes, so for ACM Chicago, you can contact our vice chair. So that's Mark Temkin, vice chair at chicagoacm.org, or for future IEEE Computer Science, Computer Society Chicago, or IEEE Vehicle Technology Society Chicago. You can also email me at alvin.chin@IEEE.org. So since this is our last event for 2020, I'd like to say thank you really all for your support. I mean, it's been unprecedented this year. I mean, we had our last physical meeting, I believe it was like in mid-March or so, before, Governor Pritzker, had the lockdown or so, and we haven't had any actual in-person events since then. So everything has all been webinars, and thank you everybody that have participated in our webinars, in our meetups, and things like that. So really, really grateful for that. The success of this, webinar would not be, without you guys, attending, and obviously give us, feedback. Because we did a lot of webinars this year, that's for sure, more than we would have done, physically. So thank you for your attendance, and Merry Christmas, Happy New Year, Happy Holidays. Stay healthy and safe if you are with friends and family, and we'll see you sometime next year in 2021. So thanks.
Thanks, Alvin. It was an excellent presentation.
Thank you.
Thanks.
Thanks, Alvin.
Bye.
Thanks.